Welcome to Study Loop.
This problem, we have a bowling ball rolls without slipping on a ramp that slopes upwards at an angle of beta to the horizontal. Treat the ball as a uniform sphere and know the finger holes. And so I'll draw the free body diagram and explain why the friction force must be directed uphill. So here's the free body diagram. We have the friction force, the normal force, the weight, the mass moment for a uniform sphere is 2/5 mr squared. So what we can see here is if we take moments about the center of mass here, we have the weight acting through it, the normal force is also acting through it. So the only torque that is acting on this the bowling ball is from this friction force. And if the acceleration is going to be this way, which we expect because it's going to be rolling down the hill, then that means the torque has to be this way also, which means the friction force needs to be in the opposite direction to what I've drawn. So it means, basically the friction force needs to be uphill to keep this thing from rolling. You might think that it should be downhill because of the acceleration is in this direction, but we also have a component of W that is in this direction too that causes the acceleration. So it's not just F causes the acceleration, but the component of W in the direction of the ramp also does. So let's see. They wanted us to then what is the acceleration of the center of mass of the ball? Okay, well we can get although we don't really need this equation for this part of the problem, but we know that the component of W in the perpendicular to the ramp, W cosine beta equals the normal force. And then parallel to the ramp we have W sine of beta plus F equals ma. And because it's rolling without slipping, A equals R times the angular acceleration. Taking moments about this point, we have minus F times R equals J alpha. And that's equal to J over R times acceleration. And that is 2/5 mr times A. Plugging in, let's see here, basically we can, the easiest thing to do would be multiply this equation times R and add it to this equation so that F's drop out, and then we can solve for A. So I didn't go through all the algebra that I had in my notes, but in the end we get that A equals 5/7 G times sine of beta. Now, that's different from if it was just a particle sliding down the hill. So yeah, you have to the fact that it's rolling slows it down actually, or reduces the acceleration. Now they ask for what the minimum friction force needs to be. So we're gonna say that so it's going to be minus F equals the minimum friction force times N, because we know this in this direction. So N is mg times cosine of beta from here. Let's see here. F, where did I get this? F from here is, minus F is minus m times A minus G sine beta from here. And then that, simplifying this, we get that is mg sine of beta times 2/7. And now we can take this and this equality, right? And we can see that m's cancel out, and we can solve for the minimum value of mu, this friction coefficient. And this tangent is sine over cosine, and so we wind up, and g's cancel out too. So we get the minimum coefficient of friction is 2/7 times tangent of beta, which means that the coefficient of friction we need to have this thing roll without slipping is something greater than or equal to 2/7 times tangent of the inclined angle of the ramp.